So let's start. It's a pleasure to continue our research seminar series today with Dr. Shota Komatsu from CERN. He will talk about tailor-made solutions to gauge theory. Thank you.
Okay, thanks for the introduction. And I'm going to talk about, I'm trying to give a kind of overview of what's happening in the field of application of idea of integrability to solve certain supersymmetric gauge theory in 4 dimensions. Because the topic and the subject is quite technical, I try to make my talk, in a sense, light in technicality. Maybe I made it a bit too light, but if you want to know more details, please ask questions. Or if you don't understand some details, of course, you're free to ask questions. All right, so this talk is, as the title suggests, about gauge theory, but actually it's also about string theory. So one common viewpoint of string theory is that it's kind of like an ultimate form of reductionism. So the matter is made out of molecules, and molecules are made out of atoms, and atoms are made out of protons, and the most fundamental object, well, string theorists believe that it might be strings. But this is not the viewpoint that I want to stress in my talk. It's rather a different viewpoint that I want to stress in my talk. So in certain situations, the strings can emerge as kind of like emergent phenomena, like critical phenomena in condensed matter physics. And the key point in this, a different viewpoint, is large N limit. I guess many of you know what the large N limit is, but let me just briefly give you a review of what the large N limit is. But before doing that, I also need to explain a little bit about what the gauge theory is. So let me just remind you that the gauge theory is a kind of one of the most important language in modern physics. So if you remember the four fundamental forces in nature: electromagnetism, weak interaction, strong interaction, and gravity. And well, clearly, 3 out of 4 are described by the gauge theory. And among these 3, electromagnetism and weak interactions are relatively easy to study analytically. And in particular, electromagnetic moment is now computed at a very, very high precision, which is 10 digits. And the result matches beautifully between theory and experiments. And on the other hand, the strong interaction is much harder, and it's kind of easy to see how hard it is. Because if you think about the mass of proton, which is a 900 MeV, but we also know the proton is made out of 3 quarks. But on the other hand, the quark mass is just given by around 5 MeV. So of course, 3 times 5 is much, much smaller than 900 MeV. This basically says that we need to understand better strongly coupled dynamics, just in order to explain the mass of proton, for example. And the key idea, of course, because it's strongly coupled, usually it's very, very hard. But the key idea for understanding this gauge theory is the large N limit. Well, at least that gives kind of analytical control over the theory. So let me just briefly review what the large N limit is. So the fundamental object in the gauge theory is, of course, gauge field. And it's in the joint representation of the gauge group. So in the case of QCD, we have a mu which is a 3 times 3 matrices. But the key insight by Hooft is that in 70s, Hooft pointed out that things simplify drastically if one replaces 3 by n and send n to infinity, which is basically the large N limit. And the reason why it simplifies is that, so let's consider the usual Feynman diagram. And in the usual theory, let's say a scalar phi cube theory, the Feynman diagram is given by this kind of expression. But in the case of gauge theory, because gauge theory comes with extra indices, it's more natural to consider what's called double line notation. And this a 3-point coupling is now replaced by this diagram, where each line denotes one of the indices here. And once you have the double line notation, then each loop in the double line, so you can draw various Feynman diagrams. And for example, you can have this diagram, and this diagram for the vacuum bubble. And each loop in the double line gives you a factor of n when you consider SUN gauge theory. And if you count gauge coupling and a factor of n, then you get like n squared here, and n squared times gm squared times n here. And on the other hand, from this diagram, you get like a gm squared times n. And in the large n limit, and what the Hooft pointed out is that if you take a particular limit in which you send n to infinity while keeping gm squared times n fixed, then from this counting, you can clearly see that the last diagram drops out. So that's this basically kind of like simplifies the set of diagrams, because you can neglect this diagram in this particular Hooft limit. And so this Hooft limit is very important because it provides an expansion parameter, which is 1 over n for the otherwise strongly coupled gauge series. And it also gives you an expansion in terms of topology of diagrams. And for instance, the leading diagrams are given by the diagrams that can be drawn on a sphere. Whereas the next leading diagrams are the diagrams that can draw on a torus, which are like this. And this appearance of some kind of like a two-dimensional surface strongly suggests that there should be some alternative description of the gauge theory in terms of two-dimensional systems or two-dimensional surfaces. But on the other hand, when Hooft pointed out this to large n expansion, the theory described in the surface remained very mysterious. And however, a big breakthrough came about when Maldacena discovered ADS-CFT correspondence. So the ADS-CFT correspondence in the most prototypical form is given by some duality between four-dimensional supersymmetric Yang-Mills theory, which is often called n equals 4 super Yang-Mills theory. This is a maximally supersymmetric Yang-Mills theory in 4 dimensions, and string theory in ADS 5 times S5 spacetime. So this is the duality between 4-dimensional gauge theory and the 2-dimensional theory, which describes the string theory. So this gives a clear proposal for what the 2D theory is. And furthermore, the connection with the 2D theory turned out to be quite useful for the computation in the gauge theory. And that was discovered by these people, and many other people developed the idea afterwards. So let me just give you the basic idea of how these n equals 4 super Mills theory is related to some interesting and special two-dimensional theories. So the basic observable in the large n gauge theory, in particular n equals 4 super Mills, which is conformal, is the correlation function of local operator, gauge invariant local operators. And one of the basic gauge invariant local operator is what's called single trace operator, where z and x are basically here. Z and x is our scalar fields, which is contained in n equals 4 super Mills. And importantly, because of the maximal supersymmetry, all these fields are in the adjoint representation of the gauge group. So therefore, you can basically view them as some kind of like n times n matrices. So in order to construct the gauge invariant operator, you can just multiply those n times n matrices and take a trace. Okay, so once you have these observables, then one fundamental quantity is the 2-point function of those single trace operators. And if you have this kind of like a correlation a single trace operator and compute a 2-point function at the tree level, and if you use the double line notation, you basically get this kind of like a diagram because each propagator connecting to operator is given by this line, like a double line, and you in the end get this kind of diagram. And if you start including interactions, then you start drawing some like a gluon exchange diagrams in between these propagators. And this diagram is topologically a cylinder, which can be understood very easily once you like fill in the holes of these diagrams. So in practice, like if you fill in the holes of these diagrams, then you get this kind of cylinder worldsheet. And you can view this two-point function as a process of like a circular string propagating in time. So this two-point function, in other words, can be understood as the time evolution of some like a one-dimensional spatial one-dimensional system. And surprising thing is that it turned out that the relevant 1+1 dimensional system is very simple, and it turned out to be an integrable system. And in practice, the relation was first discovered by computing some anomalous dimension of these single choice operator, and people found a mapping between the anomalous dimension of dilatation operator and some spin chain Hamiltonian. And that was extended to higher loop order in the subsequent progress. But what's the most important is that those 1+1 dimensional system, which is either a spin chain from the gauge theory point of view or the string worldsheet theory from the string theory point of view, if you use the ADS-CFT correspondence, is that both of these systems are what's called integrable system, and which are studied in detail in statistical physics.
Can I ask you something? So O1 and O2 could be rather different. Let's say O1 is purely gluonic, and O2 has both gluons and adjoint fermions, and yet this would be interpreted as an evolution of some loop.
Right. So yes. So because so first of all, if O1 and O2 are quite different at tree level, of course there is no weak contractions. But if you start including the like a loop corrections, as long as two operators have the same quantum numbers, there can be some diagram which connects that. And of course, in practice, what we want to do is to diagonalize these matrices, huge matrices, which have different O1s here and different O2s, and then look for some eigenvalues. And that gives you some anomalous dimension of each operator. But that is what you practically do. But if you just want to see the relation with the string theory or string worldsheet, you can basically view this like process of like starting from one operator to the other operator as a kind of evolution of some string. But the most importantly, this string is living on like a superspace. So if you have a fermionic adjoint fields in operator O2, that piece can be interpreted as a kind of string stretching into this like fermionic direction. Or in other words, from the string theory point of view, the target space of the string theory is the ADS5 times S5 superspace. So it's like a supersymmetrized ADS5 times S5 space. Okay, so let me proceed. So let me just briefly explain what the integrability is in practice. So the integrability, the hallmark of integrability is that in integrable systems, multi-particle processes can be factorized into a product of two-particle processes. For instance, if you consider 3 to 3 amplitudes, then normally, like this 3-to-3 scattering amplitudes is not related to the two particle scattering amplitudes, but in integrable series, these 3-to-3 amplitudes is related to the 2-to-2 amplitudes. And the idea is that because integrable system has infinitely many conserved charges, you can basically like shift the trajectory of the particles by acting those higher conserved charges and relate this picture where the three particles interact almost at the same point in space-time to this picture in which like you only have like you have like a two particle interacting at one point and two particle interacting at a far separated point, and the last two particle interacting at yet another far separated point. And furthermore, there are like two ways to factorize this process, and these two ways ways of factorizing must coincide. So therefore, you get some non-trivial relation between the product of two amplitudes, and that is called the Yang-Baxter equation. and all right, so and then using the integrability techniques, one can compute one can determine the first of all, by imposing the Yang-Baxter equation, one can determine the 2-to-2 amplitudes. And furthermore, using integrability techniques, one can compute the two-point function exactly. But of course, like this is just words. These are just words. So let me just give you a bit more detail of how it works in practice, especially in the simplest case. So in practice, it works in the following way. So if you consider the integral system, and states are typically labeled by the moment of excitations. And for example, like if you consider three particle states, then you have some string, circular string with some bumps at 3 points. And then furthermore, these momenta need to satisfy what's called Bethe equation, which is basically just, so if you forget this S matrix part, then this is just basically the periodicity condition where L is the length of this string. But because the theory is actually not free, but still the multi-particle process is factorized into two particle processes. So if you want to move this particle P1 along this string, then you get the usual phase factor, propagation phase factor, and on top of that, you get this product of S matrices. And furthermore, so this gives you some kind of algebraic equation for the momenta of the excitation. And furthermore, the energy of the state is given by the sum of the energy of the excitations. So in the simplest case. And of course, and there are more complicated cases in which there are some like finite size corrections, by which I mean like sometimes the energy is not factorized into a sum of, cannot be given by just the sum of energies of individual excitations, but this is the simplest case. And based on this idea, people indeed succeeded in computing the dimension of some simple operator in n equals 4 supermills, which is not supersymmetric. So because it's not supersymmetric, its conformal dimension explicitly depends on the Hooft coupling with lambda, which is g squared times n. And these dots are the prediction from integrability. So the integrability gives you some kind of integral equation, which you can solve by numerics. And this is the prediction from the integrability. And these other lines are like different schemes of approximation. And in particular, this solid line is the weak coupling approximation, which is basically based on the gauge theory, whereas these dashed lines are coming from the string theory. And you can clearly see that these integrability prediction nicely interpolates between this gauge theory prediction and the string theory prediction. And so I should emphasize that this is one of the rare rare exact results for the strongly interacting gauge series. But I should also say that this is not my work. This is the work done by these authors around 2009.
Why weak coupling approximation works so well, even to very large coupling? I see like it's not accurate there on string theory works better, but still it's kind of surprising that weak coupling answer captures the result even at very large lambda.
That is true. Well, okay, so yeah, I think it's precisely speaking, it's not true to say that this is a weak coupling answer actually, because this solid line is asymptotic beta ansatz answer, which also includes some part of the finite coupling answer. Basically, so this solid line is given by this approximation. So the approximation in which the energy of the state is just given by the sum of the energy of the individual excitations. But it is also known that that there is a correction to that, and it is also known how to compute it using integrability. And yeah, it is indeed surprising that these two lines are actually quite accurate. Also, the string theory answer is quite accurate. Okay. So these are basically the first success story in this field. But I should also say that the cylinder surface is a very special class of surfaces. And to understand more general dynamics of the surfaces, we also need to understand how the surfaces split and join. And in particular, once you understand these surfaces, you can basically glue these surfaces together to construct more complicated surfaces like torus or higher genus surfaces. So in some sense, understanding this surface, like a splitting or joining surface, is the next key step. So what does it correspond to in the gauge theory? So in the gauge theory, this surface basically corresponds to the 3-point functions. Because again, if I draw the 3-point function of a single trace operator and then draw the Feynman diagrams at tree level, I get this kind of surface. And this surface is, this kind of double line diagrams. And then if I fill in the holes of these diagrams, then I get this surface, which is nothing but a pair of pans. Here, I should emphasize that unlike the 2-point function, there is no natural interpretation as the time evolution of some one-dimensional system. It's more like you prepare 3 different one-dimensional systems and then like glue them together in the middle. So it's more like overlap of 3 different objects. And in other words, we need to understand integrable 2-dimensional system defined on this pair of pans. And this was actually never studied before in the literature. So we cannot, and in particular, people in statistical mechanics never studied that before. So we needed to invent a new method. And in order to invent a new method, so we decided to consult Wikipedia. And if you go to Wikipedia and then look at the section of pair of pans, then it shows the following sentence. The pair of pans is a double of a right-angled hexagons and along alternate sides. Sorry. And since they are isometric, and well, there are other explanations, but what's important is that the pair of pants is given by a double, like a double of a right-angled hexagon, which basically means that you can starting from this pair of pants, you can cut it along these lines, then you get 2 hexagons. And so this was like just a pictorial, seems like a naive pictorial idea, but it was actually a key breakthrough in order to compute a 3-point function. And this is indeed what we did in 2015, which is already like 5 years ago, 5 or 6 more, around more, yeah, about 6 years ago. And so in practice, of course, like this is again just picture. So in practice, what we mean by this is the following. So now we have a 3-point function, which is given by this pair of pants. And we decompose this in the following way. So the decomposition basically means inserting a complete set of state or resolution of identity. So you start from this without any excitation on top of it, and then as the next correction, you put excitation here and here, which is considering like a 1 particle state here. And then you can go on. And when you put an excitation, you should also put some propagation factor and some measure factor. And in this side, if you use this idea, then the computation of this 3-point function boils down to the computation of individual hexagons, because once you know the amplitudes for individual hexagons, then you just need to like square it and then integrate over the momenta of the excitations. And in some sense, it's similar to Sohn construction of 2D CFT, but there are also differences. And so now everything boiled down to the computation of the hexagons. And it turns out that the contribution from individual hexagons can also be determined by using integrability. And one of the key ideas for determining this hexagon is to use what's called a form factor bootstrap, which is basically very simple. So if you have a particle P1 and a P2 on this edge, and if you consider a different configuration in which the order of the particles are swapped, then you need to multiply the S matrix. And this is just saying that like when you change the order of the particles, then you always need to multiply the S matrix, which is this S matrix is the S matrix that appeared in the computation of the 2-point function. So we basically know everything about this.
Sorry, Shota, 2 questions. One, is this equation valid for any insertion of operators on the dashed line?
Okay, so these are, yeah. So this equation is valid for any excitation on this solid line. Mm-hmm. But of course, in that case, so in n equals 4 super mills, you can consider like various different insertions and various different, or in the string theory side, you can consider various different excitations. And so in that case, like this should be interpreted as kind of like a matrix equation, because like a P1 and a P2 also comes with extra indices.
But I remember that in your equation and your factorization, you also needed to insert particles on the dashed lines.
Yes, right. So there is a, okay, so here I didn't explain it in detail, but there is yet another relation which allows you to move around the particle on one edge to the other edge, which is like a crossing equation. So in the usual case of like a scattering amplitudes, if you use the crossing, then the incoming particle becomes outgoing particle. Mm-hmm. And you can use a similar idea to move one particle to the other edge.
Thank you. So last thing, if you, when you have time, can you send the slides for people who may arrive late so they can?
Okay, sure. Yeah.
Okay, thanks. You can send them to me.
Okay.
Thank you.
And yet, furthermore, by playing with this kind of form factor bootstrap and also looking at what we got from the gauge theory, because at weak coupling, and at weak coupling, we can just compute the 3-point function using perturbation theory. And we discovered that there is also like a similar factorization structure resembling Yang-Baxter, although this is by itself not at all something like scattering, but nicely, the 3-particle hexagon is actually in some sense factorized into 2-particle hexagons.
Shota, Mask, so this kind of relations which you're writing here, to what
Yes.
extent they are can be regularly derived from like other known principles, or there should be sort of some kind of new axioms which should be added, or in the result of guesswork?
Okay.
So
this form factor bootstrap itself is a derived thing, because this is basically coming from the property of the wave function of these 2-particle states. But if you want to solve this form factor bootstrap for like a 3 or more particles, then typically like there are many solutions. And in this particular case of n equals 4 super Mills theory, there was a very simple solution which has a factorization structure, and we just simply picked the simplest one. But of course, there are other solutions, and we don't know whether it's physical or whether it's allowed. And in fact, if you consider slightly different theories, for example, there is what's called ABGM theory in 3 dimensions, which is like a 3-dimensional version of n equals 4 super Mills, which is also known to be integrable. And then in that case, we almost know that this simple solution doesn't work. Although this bootstrap equation itself is valid. So this is something very special for n equals 4 super Mills. And the result beautifully reproduces the perturbative computation up to 4 loops, and in some cases actually at up to 9 loops, and also partially at strong coupling. And well, this is just one slide to give you an idea what kind of computation we are doing, what kind of result we are getting by using integrability and also from perturbation theory. And for example, this is a 3-loop answer. As you can see, it contains zeta function, then very complicated rational functions. And it's quite miraculous that the perturbation theory and the integrability both give you the same numbers. Okay, so now once we understand how the surface splits and joins, then you can also construct more complicated surfaces. For example, so far I've been talking about 3-point functions, but you can also try to construct a 4-point function using a similar idea. So for example, in the case of 4-point function, you just have a 4-punctured sphere, which is of this form, and then you can cut it in this way. So here you have 1 hexagon, 2, 3, 4. So in total, you can get 4-point function out of 4 hexagons. But there is one important difference between the 3-point function and the 4-point functions. And in conformal field theory, the 3-point function, the only dynamical data for the 3-point function is the structure constant, and all the space-time dependence is fixed by the conformal symmetry. Whereas in the 4-point function, there is what's called cross ratio, which is made out of like a position of 4 operators, and that information must be encoded in the way how we glue various different hexagons. And we can actually derive how to multiply this extra weight factor as a function of conformal cross ratio just by using the symmetry analysis. And And the upshot is that only modification from the 3-point function is that you need to multiply some like extra chemical potential or weight factor when you glue these edges. And furthermore, one can also construct higher-genus surfaces as well, like a torus surface, or even higher-genus surfaces. And also, like by taking a further limit in which the gauge coupling becomes very, very large, then you can try to like approach the dual picture, the ADS string picture. And in that picture, you can actually partially resum those hexagon series that I showed for the 3-point function. And that solution has some connection with some integrable PDE, which describes some minimal area problem in the ADS spacetime. And let me finally change a gear and talk about a bit more recent developments. So these hexagons are powerful, but they're actually not ideal. And the reason is because one needs to sum over the states appearing on these dashed edges. And so it's true that this gives you a different kind of series expansion from the usual perturbative expansion, but it's still given by some perturbative expansions. And more recently, we found some different class of 3-point function in which you can actually kind of resum some these series and get some closed form expression. But that 3-point function is slightly different from the hexagons. And in fact, the relevant worldsheet is also different. It's actually a semi-infinite cylinder. If I say it's a cylinder, then it sounds like it's 2-point function, but it's actually a 3-point function. And I'm going to give you a bit more detail in the next slide. But the upshot is that since the topology is simpler, so this is now again like a semi-infinite cylinder, one can actually sum over the state. Because this is basically very similar to the setup people in statistical mechanics considered. And you can actually write down a closed form expression, which is in terms of some kind of Fredholm determinants. And from the 2-dimensional point of view, this quantity computes the generalization of the G function studied in the statistical mechanical literature, which measures the degrees of freedom in a series with boundary. So, but let me just give you what these 3-point functions are. So more precisely, what I meant by those special 3-point functions is the 3-point function of 2 determinant operators and 1 single trace operator. And so the determinant operator is basically just determinant of some scalar field. As I said, all the fields in n equals 4 supermills are in the adjoint representation of the gauge group. So you can also write down construct a gauge invariant local operator by considering the determinant. And this is in some sense analogs of baryons, because if I just write this expression using epsilon tensors, then I get this expression. But on the other hand, in the standard large N QCD, baryons is also given by the epsilon expansion. And as is the case with baryons, it's actually not very easy to study the correlation functions of determinant operators, even in the large N limit, just because like this operator involves order N fields. But on the other hand, it's a very nice object to consider on the string theory side as well, because it is known, thanks to these, for example, this work, that this determinant operator corresponds to the D brane in the ADS spacetime. So if you consider a 3-point function of 2 determinant operators and 1 single trace operator, then that corresponds to this kind of picture. So you have a D brane emitted from the first determinant operator, and that d brane is absorbed by the second determinant operator. And on this d brane, you have string, perturbative string attached to it. And then because d brane is a very heavy object, so it's in some sense ideal classical probe of ADS spacetime. And more precisely, because the dimension of conformal dimension of the determinant operator is of order n, which is larger than 1, that means on the ADS side, that means that the Compton wavelengths of this particle due to the determinant operator is very small. And so the dual particle moves along, moves like a classical particle moving along a geodesics. And then on the other hand, this n is much, much smaller than n squared, so it does not back react to the geometry. So this is an ideal local probe which does not modify the geometry, but still goes along a geodesics. And so this previous picture was the target space description, but in the string theory description, we know that the d branes are basically given by the boundaries of the string worldsheet. And the 3-point function of the two determinant operators in one single trace operator corresponds to overlap between the single trace operators and the boundary state created by the determinant operator. So this is some like a closed string state, and this is a boundary state. You can think of it as an overlap between these two different states. And furthermore, the relevant boundary state corresponding to the determinant operator turned out to be an integrable boundary state. So therefore, we can actually determine its structure at finite Hooft coupling by imposing the boundary analog of the Yang-Baxter equation, which is basically like this given by this picture. So basically it means that if you consider some reflection process in the presence of boundary, it can also be decoupled into like one particle reflection processes, and there can be some non-trivial relation between two different reflection processes. Okay, and finally, using that idea, you can actually, so this is perhaps the most technical slide in my talk, but using that idea, you can actually determine the overlap by using the following strategy. So the first idea is to consider like a cylinder of finite size where two ends are capped off by the boundary state. And in the limit where this length of the cylinder becomes very, very large, then you can approximate this cylinder partition function by putting a resolution of identity here on the closed string sector. Then the leading term is given by the propagation of the vacuum state, and the prefactor is given by the overlap between the boundary state and the vacuum state. And in integrable QFT, you can also study this limit from the open string sector instead of like considering this closed string sector. And in that case, this is nothing but the thermal partition function of some open string. And so therefore, and the inverse temperature is given by L. So therefore, like this same partition function is given by this expression. And in the limit where this spatial length becomes very large, you can approximate this sum over state by sum over some kind of density of particles. And you can further argue that this path integral can be dominated by the saddle point. And if you compute the saddle point value of this saddle point action, then you precisely reproduce this exponential behavior. And if you further want to compute the overlap, then you need to basically compute the one loop fluctuation around the saddle point. And that is why you get some kind of Fredholm determinant. Fredholm determinant expression for the overlap. And So far, this was for the ground state, but you can also get the results for excited states by using some kind of analytic continuation. So this was basically it about the technical part of the talk. And so let me just conclude. So the conclusion is that in the large N limit, the gauge theory have alternative description in terms of two-dimensional surfaces. And in particular, if you consider very special theories like n equals 4 super Mills, then utilizing integrability, one can compute physical observables in gauge theories exactly. And in this setup, strings or 2D surfaces are in some sense emergent because we are just considering, original question was to understand the gauge theory, and the string emerged as a alternative description. And there is also some surprising connection with statistical mechanics or mathematics, which governs the integrability. And for the future direction, it will be interesting. Well, of course, like one clear direction is to develop techniques to fully solve the n equals 4 super Mills theory. And there are also like some ongoing works related to this direction. But of course, like we also need to keep in mind that n equals 4 super Mills theory is a very, very special theory. And ideally, we want to understand more realistic theories. So if from that perspective, it will be nice if we can use n equals 4 super Mills theory as a starting point from which one can explore more realistic theories. Okay, thank you very much.
Thank you. Thank you for the seminar. So now we are open to the questions. I want to ask a simple question. When you computed the 3-point function, you had a boundary state that was D1, D2. So how do you see that this a two operator? I mean, how do you see that it's just the product of two heavy operators?
Right. So I think it's probably most easily understood from the ADS picture. So in the ADS picture, this like a single determinant operator emits this D brane, and then the other determinant operator absorbs the D brane, and together they make one like a word line of D brane.
Yes.
And the string is attached to that word volume of the D brane. So that's why I wrote in this way. So the boundary state is made out of the product of two determinants.
I see. So in this picture, the proper time of the word line is
this direction.
Okay. Thank you.
Sorry. The proper time of the D brane, is that what you're asking?
Here it's in this diagram, clearly proper time is along the arch, but in the other picture, in the worksheet picture, is the green line.
Right. So in some sense, like yeah, it's a bit hard to see the proper time of D brane in this picture because very roughly speaking, what we are doing is something like if you have at tree level, what we are doing, you can also construct this like a determinant, this boundary state like object from the tree level computation. And in that case, what we are doing is that multiply two determinants and combine it to one determinant. Like a determinant of like a determinant of phi1 times determinant of phi2 is the determinant of phi1 times phi2. And then consider it as a single object. So it's really mixed in this boundary state.
Thank you. Other questions?
I have a question here. Yes. So are you saying that so these D1, D2, they're actually corresponding to one set of D branes in your string theory background?
Yes.
But corresponding to the absorbing and like the annihilating and creation of that D brane state, but not a bound state of two set of D branes, right?
It's not a bound state. It's just like a one single D brane.
Yeah. Okay. Yeah. Yeah. Another another maybe dumb question. I see in your last page of the slide about the conclusion, you said that you're doing something like the Coulomb branch. Are you saying you're doing some n equal to 2 supersymmetric field theory?
Oh, it's really just about Coulomb branching n equals 4 super-MLs.
I'm kind of confused because in the n equal to 4, you like all the scalars are in the vector multiplied, right? I mean.
Okay, so like right, it doesn't make much sense to distinguish the two, but
yeah, right.
I'm just using the terminology.
Okay, yeah, okay, yeah, sure. Thank you.
So concerning your last point on this slide, so is there any hope to use this exactly solved model as a starting point for perturbation theory around it? So if
right, of course, the most, in order to do that, we possibly need to do something like Hamiltonian truncation. But before doing that, we need to have a lot of data for the 2-point and 3-point functions. And of course, we are still a bit far from that. So the first thing we need to do is to have more data for 2- and 3-point functions in the large n limit, and then say try to like break supersymmetry in the large n limit.
So do you have an example of how these techniques can work, say, for n equals to 2? If you break some supersymmetry, not all, just as a starting point.
Right. So let's see. Right. So there are examples like beta deformations of n equals 4 super-MLs, which break some of the supersymmetry, but still keeps integrability. And of course, like these days, some people are studying more extreme cases in which you break all the supersymmetry and then take the parameter beta. So beta deformation basically deforms the superpotential, but parameter beta to I times infinity, and then get what's called fishnet theory, in which you only have scalar fields. But of course, like that theory is non-unitary, so it's a little bit sick. But I would say there are some attempts or suggestions to find some integrable subsector in general n equals 2 theories. But I don't think anyone reached any like a decisive result or conclusive results about it.
I remember there is a work by Corley and Ramgolam that calculates some half BPS state in the n equal to 4, and they have some exact correlators, right, for the giant gravitons. Is there anything you can use from their work, like to do maybe in the finite n case, right? If I remember right, they have some exact result in the finite n case.
Right. So they are studying this correlation function. Well, mostly studying the 3-point function of half BPS operators, and they are protected. So like a tree-level answer is exact, and they developed nice techniques to deal with combinatorics, which arise in the tree-level weak contraction. Because if you start dealing with the determinant operator, even just doing the combinatorics is very complicated. And of course, that gives one sanity check of the integrability result. Of course, because like unless if we give a wrong answer to that, then it means that integrability result is wrong. But
I see. Thank you.
Are other questions? So, I mean, if I can ask, what does it mean to fully solve n equals 4 super-MLs? I mean, in this theory, isn't it enough to have the spectrum and the 3-point functions? I mean, why
yes. Okay. So first of all, well, it's not enough to have the spectrum and the 3-point function of single trace operators, because if you So what we are studying so far for the hexagons is that we are just computing the 3-point function of 3 single trace operators. But that's even not the leading OPE when you bring together two single trace operators, because if you bring together 2 single trace operators, then the leading OP is the double trace operator. So so 2-point function and the 3-point function of single trace operators do not give the full information about like OPE of the n equals 4 super mills, even in the large n limit. And one good data, thing we want to do in the future is to develop some techniques to efficiently compute any point functions of single trace operator, correlation function of like any numbers of single trace operators. That would contain enough information about the large n limit.
So you mentioned Coulomb branch. So their conformal symmetry is broken. So
right.
So do this method allow to calculate then some scattering amplitude there, or what?
Okay, so what we are looking at right now is the simplest thing, which is just 1-point function of the single trace operator in the Coulomb branch. And that is basically determined by that is just again controlled by some like a one number, which is like a structure constant. Because like if you write Coulomb branch like a parameter A, you say that if you write a Coulomb branch parameter A, then the 1-point function of the operator with conformal dimension delta is given by A2 delta times some number. And we are just looking for this prefactor. And of course, this is a little bit too simple. And what's more interesting is like a 2-point functions or scattering amplitudes. And that is the next step, I would say.
But so naively, one would think if one knows everything about the theory at the origin, that in some sense already has information about what happens on the Coulomb branch, because that's this is just kind of deformation of the same theory. Is there?
Yeah. So in some sense, it's right. For example, so there are a nice series of papers by Simon Hellerman and other people in which they studied some large charge correlation functions in some supersymmetric gauge series in 3 dimensions and 4 dimensions. And in that case, they succeeded in relating the large charge correlation, like a correlation function of 2 large charge operator and 1 small charge operator to the expectation value of this operator on the Coulomb branch. But if you want to apply that method to n equals 4 super mills, then you actually need to have a very, very large charge operator, which are not single trace operator. So actually analyzing the Coulomb branch is roughly speaking of the same difficulty as the analyzing the correlation functions involving determinant operators.
Sorry, can I come back to that, the two D1, D2 determinant operators? If I think of the word line as some static D-brane, wouldn't D1 be equal to D2? And if I think of this,
yes, in some sense, like a D1 and D2 is a conjugate of D1.
Mm-hmm. Thank you. One other question is, when you talk about applications to lower n, lower supersymmetry, in perturbation theory, when computing scattering amplitude, there is some technique, I mean, it's rather systematic, in which you can write n equals 0, I mean, QCD diagrams or pure EMS diagrams in terms of n equals 4, then you subtract the n equals 2, you add the n equal 1, so you decompose them into object with larger supersymmetry than the original one. Is there anything similar? I mean, so systematic in the case of integrability, or do you need new ideas to go to lower supersymmetry examples?
Let me think. So the techniques that you mentioned are indeed used in the papers in which they try to see if there are integrability in n=2 series. So what they did is to just first do the perturbative computations using those techniques and get some answer and then see if it's integrable. But those are like in some sense very perturbative, and then what you need to subtract changes order by order in perturbation series, whereas integrability often gives you like a finite coupling answer. So I don't know how to do this kind of subtraction at the level of integrability.
Thank you. You have any other question, as basic or as technical as you want?
Hi, Shota. Thanks for the great talk. I was curious about this kind of, so either the hexagon picture or this boundary picture, if I wanted to do this for other integrable systems that maybe don't have a holographic or supersymmetry, is there like, I know you had mentioned the ABJM system, it's possible to do the hexagon as well, but you run into some ambiguities. I was just kind of curious, maybe this isn't an interesting thing to do for other integrable systems, but like, is there some, what are the sort of barriers to doing these sorts of things for other systems?
All right, okay. So, so again, right, so you can indeed actually try to construct the analog of hexagons for general integrable systems. And people actually consider something similar in the context of computing entanglement entropy in integrable systems like sine-Gordon theories and Ising models. Because if you look at this picture, then you see that like you have like 1, 2, 3, 4, 5, 6 edges, whereas the usual square has 4 edges, which means that there is some conical excess in the middle. And similar geometry plays an important role in the context of entanglement entropy, because if you want to compute the Renyi entropy, then you need to put some twist operator, and which creates extra surface. So for example, if you consider Renyi to entropy, then you need to have octagon. And that, and people indeed try to compute the entanglement entropy by solving this kind of form factor bootstrap. And that was done by Cardy and his collaborators. And again, the difficulty is in solving the form factor bootstrap, because typically multi-particle form factor doesn't have a nice solution. Whereas in the case of n=4 superimmense hexagon, we are so lucky that we had a very simple solution which can be extended to any particle numbers.
And does this boundary?
Oh, in the boundary case, indeed,
does
like
that, if that gives the same kind of path or different path to the same sort of observable, right? Or, that's proposal. Is that the proposal? If I understood correctly.
Well, it's not the same observable. It's a different observable, because like instead of single trace operator, now we have like a determinant operators, and if you take a large n limit, they are very different, because determinant operator, dimension of the determinant operator is n, whereas the dimension of the single trace operator is order 1. So, but on the other hand, this determinant gives rise to the boundary of the two-dimensional system, and that is well studied also in various other integrable models.
Okay, thanks.
Thank you. Do you have any other questions? If not, let me thank let us thank Shota again, and then we can continue informally, all right, with our discussion. We stop recording and continue informally. Thank you.
Thank you.